Dear students, welcome to another episode of Statistical Physics 1. मैं उधर से कंटिन्यू करूँगा जहाँ से हमने लास्ट टाइम मल्टीप्लिसिटी फंक्शन डिफाइन किया था. सो मल्टीप्लिसिटी फंक्शन हमने लिखा था GNS that was equal to sum over minus n half to plus n half summation over s was like that. So that was n factorial or n up factorial into n down factorial n down, ऐसे लिखेंगे हम. ये था हमारा मल्टीप्लिसिटी फंक्शन लास्ट टाइम जो हमने लास्ट लेक्चर में डिफाइन किया था. और मैंने आपको असाइनमेंट दी थी कि एक n इक्वल 10 पे आप इसको प्लॉट करें और देखें कि इसकी शेप कैसी नज़र आती है. आई होप आपने किया होगा. मैं आपको दिखा देता हूँ इसकी शेप और फिर हम इससे आगे डिस्कस करेंगे कि वो शेप कैसी नज़र आती है. सो ये है शेप जो कि n इक्वल 10 के लिए अगर आप प्लॉट करेंगे फंक्शन को तो आपको मिलेगी. और इस शेप में अगर आप देखें गौर से तो दिस इज़ it has a maximum at the center and it somehow decays pretty sharply if you go either left side of 0 or at the right side of 0. Or it's a kind of symmetric function, but somehow sharply decaying function on both sides of 0. और ये देखें आप, ये सिर्फ n is equal to 10 के लिए ये फंक्शन डिफाइंड है. अब ये तो इसकी शेप होगी इन एनी केस. इट वुड बी अ सिमेट्रिक function around the s is equal to 0 for the case of magnetic array, like this array of spins placed along one another, 10 spins just. So you will get that many type of arrangements with spin excess of 2, 4, 6, 8 or 10, and similarly minus 4, minus 2, minus 4, minus 6, minus 8 and minus 10. So this would be the general shape. अब ज़रा इसकी बात करते हैं हम थर्मोडायनामिक्स की कि किस किस्म की थर्मोडायनामिक्स इससे अटैच्ड है और इसकी वैल्यू मल्टीप्लिसिटी फंक्शन की वैल्यू कहाँ से आती है. सो आपको थर्मोडायनामिक्स से ये पता है, थर्मोडायनामिक्स में हमने ये चीज़ डिस्कस की थी. थर्मोडायनामिक्स tells us that if a system remains at constant t for an appreciably long time, I mean its temperature does not change after quite a long time, we say that it is in it's in thermal equilibrium. Secondly, we say that the system has stable physical or thermal properties. The properties do not change appreciably with time. ये तो था थर्मोडायनामिक्स में हमने ये सीखा था. अब थोड़ा सा इसको हम लेके आते हैं हमारे जो सिस्टम्स हैं, स्टैटिस्टिकल सिस्टम्स. तो यही चीज़ जो थर्मोडायनामिक्स में हमने सीखी थी कि थर्मल इक्विलिब्रियम कुछ चीज़ होती है और उसके लिए हमने माइक्रोस्कोपिकली चीज़ों को स्टडी किया था. अब हम उसको देखते हैं कि अगर स्टैटिस्टिक्स में बात की जाए तो इसका ताल्लुक मतलब स्टैटिस्टिक्स से कैसे आता है. तो अगर आप देखें ये जो GNS हमने डिफाइन किया और उसको हमने यहाँ पे प्लॉट किया, आप प्लॉट किया होगा आपने भी, मैं आपको दिखा रहा हूँ. दिस इज़ अ पीक्ड फंक्शन. सो this thermal stability is associated मैं लिखता हूँ नीचे. So this thermal stability of a system is due to a sharply defined multiplicity function. So that's a really important statement. जो थर्मल स्टेबिलिटी हमें नज़र आती है उसकी स्टैटिस्टिकल बेसिस ये है कि उस सिस्टम में जो मल्टीप्लिसिटी फंक्शन g है वो एक शार्पली डिफाइंड फंक्शन है. मीनिंग ये कि ये तो ग्राफ आपने 10 n = 10 के लिए प्लॉट किया था, तो ये भी मतलब शार्प है काफ़ी फंक्शन. ये यहाँ से अगर आप इसको देखें इसकी शार्पनेस ठीक है, लेकिन जो थर्मली ज़्यादा स्टेबल सिस्टम्स होंगे उनमें ये फंक्शन और भी स्टेबली शार्प होगा. और साथ ये कि ना सिर्फ शार्प होगा बल्कि वो तेज़ी से डिके भी करेगा. जो ही हम उसके सेंटर पॉइंट से लेफ़्ट और राइट मूव करेंगे तो वो बड़ी तेज़ी से डिके करेगा. मतलब आपको शार्पनेस वाकई दिखेगी उसमें कि दैट्स अ रियली शार्प फंक्शन. और ऐसा क्यों होगा और ऐसा किस कंडीशन में होगा, मैं मतलब इसके साथ एक छोटा सा क्वेश्चन पोस्ट करता हूँ और खुद ही मैं उसको आंसर भी करूँगा कि व्हेन इज़ देयर a sharply defined function sharply defined multiplicity function. So this happens only a sharply defined function is or occurs when I should not write is, so it occurs when the system is very large that is n is much greater than 1. So you see for 10 moments the graph is somehow difficult to plot, and if you increase to 100 or 1000, so it becomes increasingly difficult to plot such a function using this formula, this pictorial formula you see here on top. So as अभी हम जाते हैं इसकी शार्पनेस को डिस्कस करने से पहले फिर मैं सिर्फ ये बताना चाह रहा हूँ आपको कि इस लेक्चर में हम ये डिस्कस करेंगे कि लार्ज सिस्टम्स के लिए हम g को देखेंगे फॉर लार्ज n, और हम ये प्रूव करेंगे कि यस इट इज़ अ रियली शार्पली डिफाइंड फंक्शन. ये आप इस लेक्चर में ऑब्जर्व करेंगे. यू विल ऑब्जर्व ड्यूरिंग दिस लेक्चर that g of n s is indeed a very large function. It's very sharply defined function for large n, and you will actually observe this. This lecture actually consists of a little bit of derivation, and by the end of that derivation we will get to know that the function g of n is actually a very sharp function. So let's start. So if you see here we have to take factorials and factorial and up factorial and down factorial, and for small n it's okay, really easy to do that. And if n becomes very large, as I have somehow predicted here, n is very large than 1, So in that case we have to do some approximation to do the calculation somehow easier. So for large n, we use the Stirling's approximation. So Stirling approximation, एक तो आपने वो देखी थी n factorial equals n log of n minus n. So that is the one shape of or one form of Stirling approximation that we will not use here directly. We will use another form of Stirling approximation. So for large n, n factorial equals square root of 2 pi n raised to the power n exponential of minus n minus 1 over 12 n and so on, minus so on. So this is another form of Stirling approximation, the second form. And if n is large, we can ignore these higher terms, so we can keep only this first term in exponential and ignore these higher terms. So for n very large, we may ignore 1 over 12 n and higher terms. In exponential. So we have approximated n factorial in the form of an exponential function. So we write n to the power n exponential of just e to the power minus n. We write. So we call this equation, if we continue from our last lecture, so this would be called our equation 7. So it's better to keep the same enumeration so that we can refer back to equations pretty easily. So this is our equation 7, and so again, if we take now a logarithmic of log of this n factorial, then our calculations will become easier and easier. So let's take natural log on both sides. So log of n factorial equals so we'll get 1/2 natural log of 2 pi n plus n log of n minus n. We can further separate this 1/2 log of 2 pi plus 1/2 log of n plus n log of n minus n, and we can rearrange it. So that is 1/2 log of 2 pi plus n plus half parenthesis log of n minus n. We call this equation 8. So this is our log of n factorial. So if you see here in our equation here, so we have n factorial on top and n up factorial and down factorial. So we have to write similar relations for log of n up factorial and log of n down factorial. So we write simply, so we write from 8, like we infer directly from 8 that okay, log of n up factorial will be 1/2 log of 2 pi plus n up and a half log of n up minus n up. This we call equation 9. And similarly, log of n down factorial will be 1/2 log of 2 pi plus n down and a half log of n down minus n down. This we call equation 10. So we have now a complete set of these three equations, but still the story is not complete. So let's rearrange equation 8. We need it somehow. Rearrange equation 8 by how? By putting n equals n up plus n down. That relationship we studied in the last lecture. So we put this in equation 8 and rewrite it. So we had now log of n factorial will be 1/2 log of 2 pi, and here we had an n, so we write n up plus n down plus 1/2 log of n and minus n up combined with n down. So this is the kind of rearrangement. Okay, so we now introduce two terms. We add and subtract actually two terms, and that will help us to make this equation fancier. So we add 1/2 log n here, and we have to subtract it to make everything normalize, or okay, so that we end up with some better. So these terms cancel each other actually, so, but we have to introduce them so that this term, this whole equation becomes fancier. So we write log of n factorial equals, so one of these terms, 1/2 minus 1/2 n, will combine with this first logarithmic, so we get 1/2 log of 2 pi over n here, and the other term, this plus half n, goes inside here. So we write plus n half, n up plus half plus n half plus half log of n. So this is the rearrangement we were looking for. So now we call this equation our equation 11. So in the next step, we subtract equations 9 and 10 from our equation 11. So that will give us the log of g actually. So log of g was basically equal to log of n factorial minus log of n up factorial minus log of n down factorial. So when we subtract 9 and 10, we will get exactly the right hand side. So just we write it. So we had log of n factorial as the rearranged one version, 1/2 log of 2 pi over n plus n up and a half plus n down plus half log of n minus, now this will, we will write the log of n up factorial terms. So we have now, okay, so we have we are left with let's skip one term, so it is n up plus n down here. So remember it in 11 I missed one term, so I just write one term back. So it had this kind of term that I missed with a minus sign. So okay, so you just do this correction and put it back into the next equation that we are writing. Okay, so we write minus this, and now it comes log of n up factorial term, so 1 minus 1 half log of 2 pi minus n up and a half log of n up plus n up, and then come the terms from log of n down factorial, so that would be minus n down and a half log of n down plus n down. So in the next step we have to divide this term into two, so we have to disintegrate this whole term into two terms. So our next steps will be easier for after doing this. So we write 1/2 log of 2 pi over n plus n up and a half log of n plus n down and a half log of n the rest of the terms will remain the same for the time being. So I write them as such: minus n up minus n up minus n down minus 1/2 log of 2 pi minus n half n up and a half log of n up plus n up and minus log minus 1/2 log of 2 pi minus n down plus half log of n down plus n down. So these are the terms we have now. So write them carefully, and now we can cancel the terms, the similar terms with the negative signs. So first cancellation will be this n plus n up with a minus sign and n up with a plus sign, this one with this one, and the second cancellation will be this n down and this plus n down. Okay, so that these are the only cancellations, and now we just combine rest of the terms. So combination will happen between, okay, so I assign them colors, this term, this term, and this term, they will all combine, and what we will get by these terms, if we combine them, so we will get 1/2 log of 1 over 2 pi n. So the terms underlined green will be combined, and we will get as a result 1/2 log of 1 over 2 pi n. And then I somehow highlight with some other color the other combining terms. So this term will combine with this term here. How? So we will take this n up plus half common. So what we'll get? With a minus sign. So n up plus 1/2 common, and inside we will get log of n up minus log of n. Similarly, we will from the remaining terms we will take this common and down plus half common with a minus sign. So n down plus half common, and you will get a log of n down minus log of n. So this equation is getting shorter and shorter. So we write it 1 over log of 1 over 2 pi n minus n up and a half log of n up over n, and minus n down and a half log of n down over n. So we just combined the logs here. You know that, you know this property of the log very well. I write it if you don't remember. So log of x minus log of y equals log of x over y. Okay, very nice. So we have our log of g in a very short notation. So I write in a neat form here. So log of g equals log of 1 over 2 pi n minus n up and a half log of n up over n minus n down and a half log of n down over n. So we call this our equation, next equation, that is equation 12, I guess, because we had this equation 11 last time. Yes, we had equation 11. So now we write equation 12. So alright, now it's not over yet, because we wrote this equation in terms of n up and n down, but we want to write this equation in terms of s and n only. So to do that, we have to use another approximation for the series expansion. So we know from our previous mathematics that log of 1 plus x is an expansion that is minus x square over 2 minus x square over 2 plus x cube over 3, and so on. And similarly, log of 1 minus x, we had an expansion that is minus x, sorry, okay, so I just interchange this term. So for this starts with plus x, the expansion with log of 1 plus x, this is with plus x, and this is with minus x, and this is minus x square over 2 factorial and plus so on. So we will ignore, so this is the expansion we have, and what we want to do now. So if you write if you look at our functions, so we have now log of n up over n and log of n down over n. So let's rewrite them, just only logs. So log of n up over n, we can write it actually log of, in terms of, if you remember, we have n up minus n down equal to 2s. That's how we define our spin excess. So if we put now the values, and okay, and then we had, okay, n up equals n half plus s, and n down equals n half minus s. Just we replace now n up with n half plus s, plus s, and everything divided by, I write it in a better way, over n, like this. Take this value from here, put it here, and we rearrange it. Log of, if we take n over 2 common, so if we take n over 2 common from numerator, so we have 1 plus 2s over n on top, and 1 over from down we already have here, and they cancel out, these n's cancel out, and we are left with log of 1 half 1 plus 2s over n. This is for n up. Further, we can write this as minus log of 2 plus log of 1 plus 2s over n. Okay, and here if you see, there is a term that resembles log of 1 plus x here. Okay, and for log of 1 plus x, we just discussed that 1 plus x can be written like this, and further we can ignore terms with x cube over 3, because it becomes this expansion is actually valid. I write this, we can write this is equal to x minus x square over 2 for x much smaller than 1. Similarly, for L minus x, we can write it minus x square over 2 factorial in the same limit. So we just, whenever we find this kind of term, we replace it with this kind of term. So if you see here, this is the log of 1 plus x, x is 2s over n. So we can write it by using the approximation. So that is equal to now minus log of 2 plus 2s over n minus 2s square over n square. So this is our term for log of n up over n. Similar term will be written for n down over n, so that would be minus log of 2 minus 2s over n minus 2s square over n square. So this is the approximation that we will be using, these kind of terms. So I should write somehow here an approximate sign here. So this is the approximate value here. Okay, so when this is done, we just take these values and put it in equation 12. So put these values in equation 12. And log n down over n in 12. So what we will get? We get log of g now equals to 1/2 log of 1 over 2 pi n minus n up and a half. Log of g now is approximately equal to, so be careful here that we use an approximate sign here, and minus log of 2 plus 2s over n minus 2s square over n squared minus n down and a half minus log of 2 minus 2s over n minus 2s square over n squared. Now we do some simplification here. We just multiply first inside, so that we write plus n up log of 2 minus n up 2s over n plus n up 2s square over n squared plus 1/2 log of 2 minus s over n plus s square over n squared plus n down log of 2 plus n down times 2s over n plus n down 2s square over n square plus 1/2 log of 2 plus s over n plus s squared over n squared. We further do some rearrangements, so I write 1 over 2 log of 1 over 2 pi n, and I just move these terms 1/2 log 2 and 1/2 log 2 here, so I write 1/2 log 2 plus 1/2 log 2, so relatively close to each other, and then I combine other terms, like, so we have like n up to s over n and n down to s over n. So we can write it, we can take 2s over n common here, minus 2s over n common, so we'll get n up minus n down here for this term, and I just highlight them in colors. So this term and this term, you combined it and took 2s over n common. Similarly, we have n up to s square over n square and n down to s square over n square. So we just combine them also. Okay, so I take common 2s square over n square, and that would be n up plus n down combined together. And okay, so we have dealt with now these two terms, and what we are left with, so there would be one cancellation. Which cancellation we would have? So this and this term would be cancelled. So the last term will be plus 2 times s square over n squared. And this term actually we can ignore, because this is again square term in 1 over n square, so we can just simply ignore this because it will be very small term. And we keep other terms. So now we just combine first 3 terms and we just write simply, it's very easy, so we write 1/2 log of 2 over pi n. This is for first 3 terms. These 3 terms we write 1/2 log of 2 over pi n, and this term, you know, this is n up minus n down is actually 2s, so 2s and 2s, 4s squared over n. So we write minus 4s squared over n. Okay, and okay, so I missed, I think, one term here. That was this which term I missed? I think I missed one term. Okay, I did not combine these 2 terms. Okay, so I just go back, so I write here n up plus n down log of 2. So this term is missing, so I just reincorporate this term here, so that this becomes n. Sorry for my mistake, so I just incorporated this term back again. Okay, so this 4s square, this term will become minus 4s square over n, and this 5th term will be, you see, this is n up plus n down, this will equal to n, so we write plus 2s square and 1 n up from this term. This will be cancelled with the square of the denominator, so we will write 2s square over n, and then this remaining term n log of 2 plus n log of 2. That's it. So we are only left with 4 terms, and okay, so we can further reduce this, so we can write it 1 over 2 log of 2 over pi n, and minus 4s square over n and plus 2s square over n, so we will get minus minus 2s square over n from these two terms. Fine. So that is what we were looking for. So we reached where we wanted to reach. So we get log of g equals 1/2 log of 2 over pi n plus n log 2 minus 2s square over, and we can further simplify it. We just combine, we just write like this. So that is log of 2 over pi n raised to the power 1/2 plus log of 2 to the power n minus 2s square over n, and we further combine these as log of 2 over pi n times 2 to the power n. So we just combine them in one log minus s square minus 2s square over n log of g. So it is becoming a bit longer calculation, but it's worth doing. And okay, now we take anti-log on both sides, or exponential on both sides. So we write now take anti-log. So our left hand side is only g, and on the right hand side we get square root of 2 over pi n 2 to the power n and e to the power minus 2s square over n. Very nice. So using Stirling approximation, we reached somewhere very nice. So we got an approximate value of g for a large n, for very huge number of n. This is the approximation. So I should write the symbol of approximation here. When n tends to a very large number. So this function actually, this function inside this highlighted region, this function is called a Gaussian function. So normally we wrote g as, okay, we give this another equation number. So we had previously equation 12, so we call this equation 13. So our equation 13 is the approximate value of the multiplicity function when n is much greater than 1. And in mathematics, this function is known as a Gaussian function. What are the properties of a Gaussian function? So okay, I write first for the statement. The approximation of multiplicity function for a binary system in the limit of large n, that is this thing, is a Gaussian function. और Gaussian function जो है वो एक mathematical entity है. We can rearrange 13 as g equals, okay, I write complete gns, gns equals g of 0 times exponential of minus 2s square over n and here, okay, we call this equation 14, and here g of 0 is basically 2 over pi n square root times 2 to the power n. Okay, very nice. So we have reached somehow some conclusions here, and now we discuss turn by turn. So I will interpret you before you that what is going on here. So we originally had GNS as from last time. So we had GNS from the last lecture. We wrote it n factorial for so if we put now s is equal to 0 in this equation from last lecture, so Gn0 we get n factorial over n half factorial times n half factorial. We call this our equation 16. So we could not actually, for large n, we could not get correct values from equation 16. That's why we went for the approximation, and then we got this equation 14 or equation 15 and 14 and 15. So for this reason, if you now plug in the values, so if we have, for example, now the value of n is 50, for n is 50, and we get g of 50 0 1.264 into 10 raised to the power 14. This is our original value. This is from our equation 16. This is the exact value that we should get, because 50 is not a large number, so we just put it, and this gives us an exact value of G50. And now if we want to calculate an approximate value, that is G50 approximate value from equation 15, what we should get? We get 1.27 into 10 raised to the power minus 11. So minus 14, sorry, not minus 11, 10 raised to the power 14. This is our from equation 15, and that is an approximate value. So for smaller n, relatively smaller n, we get a really good match if we use either equation 15 or we use equation 16. But if we increase now n drastically large, we will not be able to calculate Gn for n, for example 1000 or 10,000 from this equation. This equation will be really hard to use for calculating factorials of 1000 or 10,000 or 1 million. And in actual systems, in actual solid systems, we have n equal to 10 raised to the power 23. So for those systems, this equation will be very tough to use. So we will use now equation 15, that is an approximate one for larger systems. Okay, so what are other properties of equation 15 or our equation 14, for example? So I write equation 14 one more time. So this is an exponential function, and to know about its width of this function, we have to see its value when its exponential goes to -1. So when this should happen, so if we take s squared equal n half, so g n s will be equal to g n 0 divided by exponential. So that is like it will reduce to roughly 37% of its maximum value. So we can use this actually. So okay, what that means, so if you want to see this, I show you what that means, how much it reduces after when s becomes n square, as s square becomes n over 2. So if you see from our graph, I show you another graph. So this is a graph for this exponential function, that is the Gaussian. So that is how the Gaussian should look like. And this dotted line, this line here, this dashed line here, this actually shows you the value when s square becomes n half. So this is like it has reduced to its 37% of its original value. So this value here at this point where this line touches this function, we say that okay, it gives us somehow some estimate of the width of this graph or width of this function. Okay, so how it's useful for us, I show you again. So the value s square equals n half gives us an approximate idea of the width or sharpness. Width is related to sharpness, no? So it gives us how sharp is the graph. So it gives of the idea of the sharpness. So but we cannot say anything directly from this. Okay, so we have to do it in some other ways. So okay, I write s square equals n half, then s will be equal to square root of n half, and if I do s over n, so this will be 1 over 2 square root of n. So now s over n is our object of interest. This gives us the relative width of the graph What do I mean by relative width? For example, let n is of the order of 10 raised to the power 22. We have a huge system in which total number of spins or total number of atoms are lattice points are n 10 raised to power 22. So in that case, s over n, that is 1 over under root 2n, will be of the order of 10 raised to power minus 11. So if you see, what do you mean by 10 raised to power minus 11? It shows that it is a very, very sharp graph. The smaller this number is, the sharper the peak of the graph is. And it's a relative width, so it has another meaning also. if you plot a graph here of this system, so I give you a rough clue what does this mean. So if you plot a graph and if you say that this scale is roughly, I think, 10 kilometers roughly, this length is roughly 10 kilometers. So what that means is that the function is so sharp that you will see only a spike here and you will see nothing either to the left or to the right of this in the 10 to 11 kilometers range. Remember, this is our G here on the y-axis. So you will see a very small, a very sharp but small peak in comparison with this width. So this is the Gaussian actually. So your Gaussian is a sharp peak but really relatively small width in comparison with the total span of the graph. So this is how you will see. And now we have defined that the multiplicity function that I talked about in the start, what I mentioned, that our system is for large n. Our multiplicity function has turned out to be a very, very sharp function in this case. So whatever I talked in the beginning, I am just repeating this. So in the beginning we speculated that if the n would be large, the function would be sharp and the system would be stable. And by the end of this lecture we actually proved that our approximation for the multiplicity function at large n is actually very sharp. It's a Gaussian. The binomial itself is not sharp. Okay, so we studied about binomial and we read about it in the previous lecture, and we know a couple of lectures ago. So we know that it's a symmetric function, but it's not a very sharp function. But as soon as we go for large n, it becomes sharper and sharper, and its relative width decreases very sharply, and that's what we wanted to say. So our system, in the conclusion, our system with large n possesses stable values of its physical properties. So which physical properties it has stable values? We haven't seen any actually. So in our system here, where we are studying our magnetic spins arranged in a row, so which kind of properties you expect here? I have a simple question for you. Which types of stable properties do we expect in this case? So we have already defined that this system, when n is very large, it's a stable one. But which properties are stable? We will see this in the next lecture. And we will see that, okay, for this system, spin is important. Spin is an important property. And we may check the average value of S square during the next lecture. And what do we mean that it's stable? Okay, so that we will also discuss in the next lecture. Okay, one thing is for sure that we will say, okay, it has some average value, and since we have computed it using a Gaussian for a large n, so it is a stable one. But what actually it means that in terms of thermodynamics and the properties of the system, we will also discuss this during the next lecture, what it implies, how we can understand it in terms of physics. So till then, I say ciao.